So good morning. So it's officially time to start. Please fantasy to make yourself comfortable, and we can start the session right now. Okay, good. So this is the Lwig session at IETF 19.7, and make sure you are in the right room. So because this is an IETF working group meeting, so please be aware of the rules of the process of the IETF. We will use basically the collaborative note-taking on the Etherpad. Please visit the link to note what you have said during the meeting. But we need someone who can at least lead the editing on the Etherpad. Who can help? Okay, thank you, Rahul. We need a Jabber Strapper. Because on the Meet Echo, who can forward questions and yeah. Okay, thank you, Jing. Okay, I will hand over the blue sheet. It's very important to sign them. Yeah, so we can start. We have updated the milestones, so basically you can check the mailing list and the charter text on that. We did have a lot of working items that failed to have come out with the working group last call because of the lack of the views. But we are anyway. I will ask the ADs how to process on this. But hopefully the upcoming document we can be more smooth to move them forward. So here is the agenda today. So basically we have the first talk from the Carlos on TCP over constraint node. This has been a draft. I think this is second version of this draft. We have some discussion today because suppose Lwig is the home of this draft. And the second talk is from is an update report from Mohit on the lightweight implementation experience of the crypto on sensors. And the third talk is from Rahul Jadhav, which is a relevant topic, but there's not a mapping draft yet. But the issues that will be discussed today will be relevant to the implementation guidance here. So that's why we have a slot here. Any questions to the agenda? Okay, so far so good. So we can hand over to Carlos on the first talk. You can use this one. Box.
Okay, hello, good morning. My name is Carlos Gomez. I'm going to present the status and last updates made to the draft entitled TCP over constrained node networks. And my co-author is John Crowcroft from the University of Cambridge. So first of all, let's take a look at the status of the document. The initial version of this draft was presented in Berlin in 2 working groups, Lwig and also TCPN. At that moment, we didn't have yet a confirmation of which would be the home working group for this document. However, in Berlin itself, we got this confirmation that Lwig would be the working group for the draft. And we submitted an initial 0.0 version of the draft, including Lwig in the name of the file, which, however, didn't include any other modifications. And all the actual updates that we have applied are in version 0.1. By the way, these updates try to address most of the comments that appeared after the initial publication of the draft. And I'd like to thank everyone for the great feedback that we got. So let's take a minute to remember which is the motivation for this document. Today we have that there are several application layer protocols which are being used for IoT scenarios. For example, we have the constrained application protocol, which was originally designed over UDP. However, there's a co-op over TCP specification in progress, motivated mainly by the need to overcome middle box problems. Then also we have HTTP 2 and even HTTP 1.1, which are in some cases being used and considered for IoT. Also XMPP is used in some IoT scenarios. And for example, MQTT is a non-IETF application layer protocol, which is, however, popular. And all of these protocols are using TCP. So while TCP had been a little bit neglected or even criticized regarding its possible use in IoT scenarios, we have that it's actually being or will be used in many IoT scenarios. So the purpose of this document is to offer simple measures for suitable TCP implementation and operation over constrained node networks. So let's go through the updates in version 0.1. First of all, RC2119 language has been removed. So the idea is that the purpose of the document is to explain how TCP can be used in constrained node networks. So what we are not trying to do is something like proposing a new TCP variant. In the introduction, XMPP has been added to the list of application layer protocols used in CNNs which are using TCP. Then in section 2, which shows the characteristics of CNNs which are relevant for TCP, one detail has been added, which is the fact that often the link layers which are used in this kind of scenarios are offering low transmission rates. This can be roughly categorized as typically below 1 megabit per second. This is relevant in the fact that this gives the idea that throughput is typically not the main concern in this kind of scenarios. We have added a new section called Scenario, section 3, where we try to illustrate which is the main scenario that we are considering for the use of TCP over constrained node networks. And what we have is the scenario comprises constrained devices which communicate with some other unconstrained device, possibly, for example, as part of cloud infrastructure. So these would be the 2 TCP endpoints, the constrained device and the unconstrained device. And often we have to overcome, we have to traverse a middle box, which may be in between the constrained device and the unconstrained device. This kind of scenario is asymmetric in several aspects. First of all, there's the obvious difference in terms of resource availability in comparing constrained and unconstrained devices. And on the other hand, assuming that a majority of constrained devices will probably be sensors, then the amount of data sent by the constrained devices is probably going to be greater than the amount of data received by these constrained devices. Then section 4 provides the recommendations and guidance on TCP over these kind of scenarios. We have added subsection 4.1, which explains that typically the TCP connection would be initiated by the constrained device. This is in order to better support energy conservation techniques by the constrained device. Then in subsection 4.2, we have the text that discusses about the maximum segment size. And we have added text explaining that if there's a link layer which offers a not so constrained MTU, so for example, an MTU greater than 1280 bytes, it's still good to set the MSS so that the IPv6 datagram size does not exceed the 1280 byte threshold. So the idea here is to avoid issues with internet links which might not have an MTU greater than 1280 bytes. Subsection 4.3 focuses on the window size. In the previous version of the document, we were kind of mandating the use of a stop and wait approach. Now we have relaxed that, and we are recommending a single MSS window for receive and transmit operations as a lightweight approach. However, we also explained that if a device can afford it, for example, because it has enough memory and processing power, a 5 MSS window could be suitable because this might allow to use fast retransmit and fast recovery. Then in subsection 4.4, this focuses on the retransmission timeout. Here, well, we have actually kind of a question, because we would like to recommend the use of an alternative RTO estimation algorithm. So the idea would be to use something different from what is the actual RTO scheme used in TCP, which is defined in RFC 6298. We have some experience with COCO, which is an adaptive congestion control algorithm, which is now a working group document in the core working group. And this has been designed specifically considering some of the characteristics found in constrained node networks. And we believe that we have some evidence that this is working better than approaches based on 6298. So here we have a question which I don't know when or where should this actually be solved, but we'd like to find out how to proceed, because the use of COCO is actually conflicting with several TCP specifications, with several masts, such as, for instance, RFC 6298. And also in COCO, we are using weak RTTs, so this is in conflict with the current algorithm. So this is something that we'll need to find out how to proceed. Then about the TCP connection lifetime in subsection 4.5, we have restructured a little bit the section, and we have added a subsection here. So the main idea was that in order to minimize the overhead in the communication, the ideal situation would be to have a permanently open TCP connection between the two TCP endpoints. However, this is probably not going to be feasible, considering that often we'll have middle boxes such as firewalls, which may perform deletion of filter state records, let's say earlier than expected. And this might lead to breaking a TCP connection. So in addition, we have the TCP keep alives are probably not going to be useful to solve this issue, since the default timeout for the keep alive is 2 hours, and it cannot be lower than that. So possible approaches rely on having application layer heartbeat messages. And then there's another approach which was suggested by Abhijan on the list, which is the use of TCP fast open. The idea here would be, okay, if we have a middle box which is creating these problems, then okay, we can try to initiate a new connection every time we have to send new data. However, if we use TCP fast open, this would be good in terms of low overhead, because data can be carried in SYN and SYNAC segments and also be processed immediately by the receiving entity. And however, there's something to take into account. That is that for security reasons, a cookie must be obtained by the device which is going to initiate the connection. And this cookie, which may have 4 or 16 bytes, has to be included then in SYN segments, and also it has to be refreshed from time to time. So here we should try to compare what is better: to use TCP fast open even if we have the cookie and it has to be refreshed, or to open a new connection every time we have to send new data with the traditional three-way handshake. And we did some calculations, and what we found is that as long as the cookie refresh rate is below the new connection rate, then it is really more efficient to use TCP fast open. Then in subsection 4.7, we've discussed TCP options, and the text has been modified a little. Now we explain that for single MSS, for devices that use a single MSS receive or transmit window, the idea is not to support window scale, TCP timestamps, and SAC or SAC permitted, and to ignore these options if received. However, for less constrained devices, for example, with more memory allowing for a greater window, then the idea is that selective acknowledgements may be positive, may be good, since they can avoid unnecessary retries, and they may allow reducing latency, bandwidth, and energy consumption. We have to take into account that we are dealing with lossy scenarios, and therefore SAC, selective acknowledgements, may be useful here. We have added a new subsection which discusses delayed acknowledgements. The idea is that, on the one hand, a device that advertises a single MSS receive window actually needs to avoid supporting delayed acknowledgements in order to avoid contributing some extra delay to the RTT. This additional delay might be up to 500 milliseconds. And in general, delayed acknowledgements would not be really recommended in constrained node networks, since traffic is mostly of transactional type, with a transaction size often below or maybe in the order of the MSS. However, it's true also that it could be useful to use delay acknowledgements to reduce the number of acknowledgements involved in bulk transfers, for instance, in firmware updates. However, these kind of interactions are relatively infrequent compared with the rest of transactions. Then in section 5, we have security considerations, which is still fairly empty. However, we have included that if TCP fast open is used, security considerations of its specification, which is RFC 7413, apply. Finally, we have added an annex to the document. The purpose here is to document which are the characteristics of existing TCP implementations for constrained devices. So we have subsections for micro IP, for lightweight IP, and a placeholder for Riot. And for the moment, we have an overview for micro IP and lightweight IP. So for the first one, micro IP is a TCP IP implementation intended for 8 and 16-bit CPUs with a code size around 5 kilobytes, which comprises checksumming, IP, ICMP, and TCP. And here there's a global single packet size buffer for incoming packets. However, there's no buffer for outgoing data. And this means that applications that might need to perform retransmissions have to be responsible themselves for this kind of function. On the other hand, the MSS is not modifying during a connection, And the idea is that a stop and wait approach is used, which in addition to other advantages in terms of simplicity that we have discussed, this also avoids sliding window operations, which use 32-bit arithmetic expensively, which are, however, expensive on 8-bit CPUs.
Rahul Jadhav from Huawei. So can you please, yeah. So you mentioned no buffer for outgoing data. So I think I would have to contradict here because I feel there are 2 buffers used in UIP as compared to 1 buffer in UDP for UIP TCP. So the reason being that you cannot really, application doesn't have any control over the sequence numbers or MSS values at the TCP layer. So it has to keep the buffer, and that buffer is kept into UIP connection structure.
Yeah, so I would agree with you. I think maybe what we might need to, or I might need to do is to check maybe there's a matter related with versions of micro IP. So I suspect that the data here refers to maybe some older version. This could be.
In Quantiki 2.6, there was a single buffer used for incoming as well as outgoing data, the UIP buff. But at the same time, Quantiki 2.7 introduced another UIP connection on per socket basis. They introduced another buffer because there was no way possible for application to maintain the sequence number and then MSS by itself.
Okay. Yeah. So yeah, thanks for the comment, and definitely we have to be careful and address this in subsequent revisions. So yeah, so for lightweight IP, this is a TCP/IP implementation also for 8 and 16-bit CPUs. However, this is not so constrained. Actually, the code size is greater. Depending on the platform, it could be between 14 and 22 kilobytes, out of which the TCP code size is between 9 and 14 kilobyte. So here we have buffering of incoming and outgoing data, so applications don't have to, well, can be decoupled from the network stack. And a transmission window greater than a single segment is supported. And functions such as slow start, congestion avoidance, fast retransmit, and fast recovery are also supported. Also, we have some issue here about possibly the versions of the implementation, because in some older version of lightweight IP, selective acknowledgement and window scale are not implemented. However, in a more recent version, these are supported, as mentioned, for instance, by the chair on the list. So this is something we'll need to solve in subsequent versions of the draft.
I think that's, from Jabber?
Yeah, from Jabber, Michael Schaff. And there's a question.
Speak to the mic.
Sorry. Okay. So the question from Michael Schaff, and the question is why the document recommends a lot of aspects not followed by LWIP stack.
Well, I think it depends. For instance, in Riot, which is text that is to be provided in subsequent versions, I know there has been an implementation which is really using the single window, single MSS window. So it depends. I understand that possibly for subsequent versions of the draft, it would be good to try to determine which recommendations would be more suitable, for instance, for class 1 devices, which might be better for class 2 devices, and so on. So I think possibly we can try to do this exercise, and instead of providing these broad, rough recommendations, try to be a little bit more accurate and precise and say, okay, this thing would be useful for class 1, this would be good for class 2, something like that. Okay, so yeah, as shown here, we plan to add some text about the TCP implementation in Riot. And yeah, so this is the end of the presentation. And actually, we would like to ask to the working group whether you would be in favor of adopting this draft as a working group document.
So any more comments?
Suresh Krishnan, SAD. So have you run it by TCPM after you've made the modifications to the draft? Have you had a chance to talk to the TCPM people after you published the new ref?
Well, actually, Michael Scharf, well, the draft was published on both lists, at least the notification, and Michael provided several comments, which we still have to actually address.
Okay.
But we do plan to take into account his feedback, which is very useful for us.
So I think it would be good, like, so go ahead with the adoption call that you want, but before you submit as working group document, like, please make sure that Michael's comments are addressed at least.
Yes.
Okay, thanks.
Definitely.
Okay, great. So,
Yeah, Thomas Schmidt, a quick note about the riot. So the TCP implementation is in the testing phase in the moment, and it should be released in the next release, which is early next year. So,
Thanks. That's great.
Yoshifumi Nishida, one of the co-chair of the TCPM working group. So I'm wondering, addressing comment, Michael's comment is okay, but how do we continuously reviewing the draft from TCP's point of TCPM's point of view? Is there any idea?
Suresh Krishnan again. So, like, if this document gets adopted here, I would really like to run the working group last calls on both the groups. Does that make sense? So, like, you won't have any sync for a little bit, right? But when when the working group feels the document is ready, we're going to bring it back to TCPM to check if everything's still okay.
Okay, thank you.
yes, I think we have another example that we can learn from. For example, there is a TCP tune for the HTTP working group, for the HTTP draft, which is actually handled and in the HTTP working group. But actually, I think the last call is also handling on both working groups. So I think we have a pre-experience on that, so we can just follow the examples there. So at least I can ask how many people had read any version of this draft? Yeah, about 10. Good. Any people want to continue review this draft? Okay, 5. Okay, great. Continue, 6. Great. So let's handle to the list. Okay, good plan. Thank you.
Thank you.
Next talk is Mohit. Please be quick. Go ahead.
So hello everyone, I'm Mohit and I'll be presenting our draft on practical experiences with public key cryptography on 8-bit microprocessors. And this was work done together with my co-authors Yari, Ari and Heidi. So I did present this draft in Berlin, but just for the benefit of those of you who are not there, I'll very briefly and quickly go through what the draft is all about. So our goal for this work was to see how hard it is to do public key cryptography on very small devices. So we wanted to see 3 things. So as a developer, what kind of libraries I have, are they easily available? Is there some open source libraries available, and so on. Then the next goal was how hard it is to actually use them. So how much hacking does it require from me as a developer? And once that is done, it's up and running. What kind of performance can I get? So what kind of performance numbers can I expect from these libraries? So for all the work that we did, we used a Arduino Mega board. It has a Atmel 2560 processor. So it's 8-bit processor, has about 8 kilobytes of RAM in total. So yeah. So the first thing that we did was see the performance of RSA, and no surprises there. For smaller key sizes, you were able to get reasonable performance, but for anything, for bigger key sizes, the performance was undesirably slow. So you wouldn't probably use that. And it took quite a while and a lot of memory to do RSA for reasonable key size that you would use. So something like 2048, which is what is recommended, the execution time was so large that probably you won't want to use it in any real scenario. And then we found 4 libraries that do elliptic curve cryptography. In particular, we looked at elliptic curve digital signature algorithm. And again, no surprises here. Elliptic curves perform much faster than RSA, use smaller key sizes, smaller signatures. And one interesting thing to note was that if you really get down to implementing things on these small devices, you can actually do a lot of things. So for example, for one of the curves, some of the math was implemented in assembly that was for that 8-bit microprocessor, and you were able to do signature, hash the message and sign it within 261 milliseconds, which for many IoT devices, 261 milliseconds is reasonable performance. And this was within 3,000 bytes of RAM. So you can get reasonable performance even on the smallest devices. Then of course now the IETF is working on specifying new Edwards curve digital signature algorithm, and I think this is what is recommended for IoT devices when they are implementing new applications. And we found again like 2 libraries that are available in the public domain, NACL and MicroNACL, and they do performance on the same board, and you can do signing in about 1.5 seconds and verification of signatures in about 2 seconds. So again, depending on your use case, and it might be too slow or it might be reasonable performance. So if you think of a sensor that wakes up once in a while and sends a signed update, maybe this is acceptable. And of course, like if you really want to reduce it further, probably if you implement things in assembly, you can probably even reduce these numbers further. So the reason why we wanted to do it was we wanted to build an example application where you wake up once in a while and send a signed update to the proxy. So instead of this sensor device acting as a server, the sensor device actually sends a signed update to the proxy, and any client that is interested in the data will go and then fetch it from the mirror proxy. And you would still get end-to-end data authenticity and integrity. So we implemented this whole application on the same platform, and here are some numbers. So implementing co-op, implementing all the crypto, implementing all the UDP, everything was less than 5,000 bytes. And yeah, I mean, we didn't really try to optimize the flash memory consumption, but if you want to, you could probably get rid of a lot of lines of code even there. So what we learned, well, the first thing was that we chose this platform was on purpose. It was unnecessarily restrictive. So what we wanted to show was that if you can do it on an 8-bit device, you can for surely do it much more easily on a 16-bit and a 32-bit microprocessor. And just because of economies of scale, probably you would use a 32-bit processor because they are actually cheaper than the 8-bit devices these days. The next thing was it actually makes sense to do computation on the processor because it consumes more energy to turn on the radio and send packets on the radio. And there is no reason why you wouldn't choose a platform that lets you do the security that you need. So yeah. Then the draft has like a lot of details on feasibility of public key crypto. How do you do message freshness? If a sensor only wakes up once in a while and sends a message, signed message, how do you protect against replay attacks? So how do you still use sequence numbers or timestamps and things like that, especially in this unidirectional communication? There's discussion on symmetric key versus asymmetric crypto, and whether you do crypto on link, network, transport, or application layer, and what are the trade-offs, and whether you do it on one of the layers or all of the layers, and how does it combine. So I won't go into the details, but come to what has changed since the last version. So in the IETF in Berlin, we had a working group adoption call in the group, and there was interest, and this was later confirmed on the mailing list. I got a lot of feedback both on the mailing list and off the mailing list. So I would thank Akbar, Rahul, Daniel, John, Abhijan, Renzo, and Raghavendra. One big reference was to this DTLS group keys, and we have removed that reference. So that was a mistake on our part from the author, so that reference is removed. There was a ton of editorial suggestions, so we have fixed that. Also, we refer to the mirror proxy draft, and it would probably make sense to update it with the pub/sub broker draft. So that we would do. Then another comment we got was we show a lot of numbers for key sizes that are not necessarily secure, and that is just done to give you a perspective or more of a reference. So at no point do we recommend using anything that's not secure, and we already do state that, but we will state that even more explicitly. So don't use smaller key sizes. Those are just there to give you an idea of how fast and slow is it based on the key size. So of course the author thinks that it's ready for working group last call, but we need like a couple of thorough reviews to iron out any minor issues that remain.
Yeah, Carsten Morman, we're seeing all these faster CPUs, but I think one other interesting thing that has been happening in the last couple of years or 3 years is we are seeing much lower power radios. So I'm not sure that the conventional wisdom, which was avoid radio usage at any cost, you can use a lot of computation for that. Whether that isn't actually shifting back a little bit. So I think it would be nice to have some more current numbers on this. I think most of the numbers we have on this are with 2005 style radios, and people have been very good at reducing the power requirements of radios recently.
So do you think numbers would help, or do you think we should? So I'm asking you for suggestions. Is it numbers, or do we tone down, or do we say that it might be faster than sending packets on the radio in some cases, but not all cases? Or so what kind of radios would it be?
I'd rather send a packet than let my CPU run for 2 seconds.
Okay.
So there is a trade-off there, and the old wisdom was it's almost always better to avoid sending a packet, and that is getting a little bit different. So having numbers for that would be great, but maybe if we don't have that, just saying that
Okay, so tone it down a bit.
maybe the conventional wisdom is being modified a little bit by recent chips would also be useful.
Sure. Is there any particular radio that you want us to look? I mean, not just for this draft, but for me, like personally, to know, like to experiment in future. Like I have played around with Zigbee on the same board, but I mean, those are still like old.
Zigbee radios often are chips that have been designed 10 years ago. So yeah, I can look up whether
Sure.
I can find
Okay.
appropriate.
Okay, but thanks for the suggestion. So anyone else who wants to review the draft, please, I'm happy to receive feedback before this goes into last call.
Yes, any expert to view the draft if we head for the working group last call?
I just have to arm twist them into sending their reviews.
Probably they have already do that.
Well, I'll ask again.
Okay, so
offline.
yeah, we will ask on the list. We don't want to be silent during the working group last call.
Yeah.
Okay, thank you.
Yeah.
So it's Rahul, it's your turn. So this is not a charter item, but I think the scope of the work is related to implementation experience and guidance stuff. So that's why we hold this talk now.
I'm Rahul Jadhav from Huawei, and the presentation is about neighbor management policies. there has been some discussion that happened on mailing list, on role mailing list, as in, if the node density is higher, how do you control the neighbor cache or the neighbor table? So what this presentation describes is how is it handled currently in different open sources, some literature analysis, as in what does the literature say, and what we eventually ended up doing in one of our practical deployments. So the challenge is that the network size can be huge, and even though the network size is huge, there is some control over the maximum number of devices that can be connected in the network or can be attached in the network. But there is absolutely no control over the maximum density, the node density. It varies from deployment to deployment. If you keep a neighbor cache of 30 entries, well, if the neighbor node density is 100, then it's going to overflow for sure. In that case, which are the best entries to evict? Now, that is the decision that an implementation has to take. Now, there is one sample policy that we have described in this presentation. So some of the current neighbor management techniques or policies that are followed, for example, by Contiki uses least eviction policy of removing the least recently used entry. So the biggest problem with this is you will get, or you might get, route downtime. So the traffic will be impacted if the node density is higher than the neighbor cache size. Riot does it on first come first serve basis. The problem with this approach is typically in a wireless network you will have DIO storm. Now, for the sake of this presentation, I'm going to make use of our Ripple oriented network or Ripple based routing protocol and a key management protocol also. So we take a holistic approach towards solving this neighbor management policy. So what is the expectation of the neighbor management policy eventually? So it's expected that, yeah, you will end up in a suboptimal behavior or suboptimal performance, but there should be some deterministic way of allowing all the routes to be established in the network finally. So the expectation is that finally the network should be formed. So currently it's very difficult in Contiki, or I've only reviewed the code of Riot, but in Contiki it's not possible to have a node density which is higher than the neighbor cache table. So some of the literature analysis that I did, so most of the literature talks about the link estimation techniques. So how do you compare the link quality of two neighbors and then prioritize one neighbor over other? But in case of dense deployment, this will seldom come into picture because the network is dense, all the neighbors are close to each other, so the signal quality is going to be good anyways. So it's not only about the link estimation per se here, but also about prioritizing the neighbors.
Probably we should move a little bit faster to leave some time for discussion.
Oh, sure. All right, I'll try to. So we tried to take a holistic approach here. We tried neighbor management policy in context to a Ripple-based network plus the PANA-based key management protocol. So essentially, we used a PANA mechanism for key management, which is used by Wyson. So the deployment that we have targeted is a AMI network here. So cases, now usually the neighbor cache table is populated using neighbor discovery mechanisms such as NSNA. But in case of constant networks, most likely this signaling is avoided and the neighbor table is populated using one of the existing messages from key management protocols, for example, the discovery protocol for key management, or based on the relay messages, Ripple messages. So there are three cases in which, so the first case in which the neighbor table update happens is while PRE selection is being done by PAC. So PAC is PANA client, PRE is the PANA relay element. So there are different names to this. I just came from Sixtish and Anima working group meetings, and they call it join JA and JCE. Join assistance and assistant and join coordination element. So join coordination element essentially is this. This is the JA, join assistant, PANA relay element as it is called here, and this is the PANA client, the new joining node. So these are the cases in which the neighbor table updates here. So there's an example table given over here for N3. So it has 4 entries. So 2 entries, N1 and N2 are our ripple parents. N5 is the ripple direct child. Now this distinction is this. It is very important to distinguish this fact that it's a direct child, because only the neighbor entry for the direct child is stored. So through N5, N6, and N7 are going through N3, but these entries N6 and N7 of course are not there on N3. So N5 is the direct child for N3, and the state for PAC or the PANA client is authentication in progress. So this relay element at any point of time does not know the state at which the authentication signaling is in. So it does not know whether the authentication is completed, is it in access phase or join phase. It's not aware of that at all. So the insertion. So what are the different neighbor management operations that have to be done? Insertion, eviction, and reinforcement. So insertion, how do you insert? The simple logic of if the table space is available, you insert the neighbor entry. Now, well, that's going to cause problems in case where Ripple's DIO storm is going to cause all the neighbor table entries to get full. Parent selection procedure may result, in case of Ripple, the parent selection procedure may result in the same parent being selected by all the child nodes. So in which case, all the DAOs will go through the same parent. So there is another problem there. Similarly, the neighbor discovery, the PRE discovery, so the PANA relay element discovery may result in the same PRE being made use of by all the PANA clients. For eviction, the issue, one of the biggest issue with the eviction is a routing child, direct child. It is difficult to evict it because there might be dependent child based on the routing direct child. For example, in the previous slide, we saw that if N5 is evicted, it has direct impact on N6 and N7 as well. So it's very difficult to evict such a neighbor. Evicting non-preferred parent information is usually possible without much immediate implication. So this is one of the key point that is highlighted here, is that it is possible to evict a non-preferred parent. For example, on receiving a DAO, one can evict the least effective parent entry from neighbor table. The third part is reinforcement. So you have the link estimation, but you have to keep updating it. So whenever you get a message, you have to keep updating the estimation, the quality parameters. So yeah, so it can be done based on whenever you get the next DI message or any traffic packet from the neighbor. The other thing is, how do you take back the neighbor table entries? So how do you clear the neighbor table entries? So one of the problem is there, the route invalidation is very important, because if the routes are still the stale routes may cause major problems with the neighbor table entries. The PRE neighbors, now I've mentioned this already, that the PRE neighbors, the PRE by itself is stateless. It does not keep any state with regards to PANA client. So it is no way possible for the PRE to know when the authentication signal is finished. So there is no way it knows when to clear, how soon to clear the neighbor table entry for the corresponding entry for the PAC. Now, some of the recommendations that we have done, or some of the observations that we had is, it's better that to make a reservation for routing direct childs and for PRE authentication. Now this is the most easiest approach that can be followed, a reservation policy. But the best part here is, if these entries are not occupied, the Ripple parent neighbors can still occupy these entries, because the important fact here is that the parent node entries can be inserted at will and can be removed if necessary, can be evicted if necessary. There are some mechanisms in Ripple already present to reject the routing direct child DAOs. So if a DAO is sent from a direct child, then you can reject it using a NAC. Similarly, for PANA client, there are ways to reject the neighboring entry by using a result code AVP. So essentially, this is the way in which, so we finally ended up reserving routing direct child entries and PRE authentication. So maximum number of authentication sessions that can be in progress at any point of time is determined by this number. So what is the impact of this neighbor table management policy? So if we don't assume that there is any restriction on the neighbor table size, ideally we might get this network. But if with neighbor, with assuming that the max neighbor table entries are 3, you will end up getting this sort of network. So the point that I want to mention here is, now this is a suboptimal behavior. If you see, N3 now has to pass its packet through N2 BR. But here, so there is one extra transmission here. So it is suboptimal. But then there is a trade-off here because the memory is not available. Yeah, so this is the problem that we faced in our deployment and pilot program.
Michael Richardson, wow, this is great work. Is there going to be a draft attached to this? I was looking for more details. And
well, yeah. So the idea why I presented this PPT is to check if there is already any work been done in this context.
Okay.
Yeah, and if necessary, then I will work on the draft. So basically, there are already implementations. If there is any other implementation available which solves a problem in a different way,
I think we should have a draft. And I don't think I think it may be very welcome in Ripple as in roll. Can you go back a couple slides?
Sure.
I just had a couple of questions understanding your analysis. Go back, sorry, a couple more of the diagram. That one. Does N3, are you thinking that N3 was in radio distance of N6 and N7? So it might have heard them, but that they didn't pick it as a parent?
No, here the assumption is N5 is only reachable, N3 is only reachable to N5.
Right, but I'm saying N6 and N7 could well have heard a DIO from N3, but the DIO from N5 was much better link quality, so they picked it.
Yes.
Right?
Quite possible, yeah.
And also in a storing network, at least, N3 would know that N6 and N7 are attached to that direct child, and so could bump the priority of keeping that direct child. So you're saying we always want to keep direct child anyway, but the number of things below there could also rank the direct childs if you ever found that you had to push direct children out. Okay, which would be terrible to do, but it might cause the network to rebalance.
Yeah.
Okay, if you did that, but that would tell you how bad it was in terms of the different things. Non-storing mode, we have no idea.
Yeah, but
right?
yeah. That's a valid point. Yeah. So.
And you also said that you didn't think that you could tell when the auth was done.
Right. On the PRE. Yeah.
So if you looked at a PANA system, and I'm not actually, I actually think that's not true, because I think that if you're doing PANA in the way that I think that it's being done, that N3 actually will receive from the auth server a key set that it's supposed to, that it gets one part of a key and as the authenticator, and the PAC, the new node, gets the other part of the key. So it actually will hear when that thing is thing, because it's going to have a new key. If it's not PANA, right, then one of two things will happen. Either the new node will negotiate a key using, I don't know, mesh link exchange or 15.9 or something. So actually it would know that the new node has now established a key and is no longer authenticating. Okay.
Yeah, so that is a separate signaling. But
so there's a separate signaling. There's other clues in there. What I'm saying is there's other clues in there that can feed that, what's going on. And the key thing is that the neighbor table has some other pieces but very clearly, I mean, it needs to reserve a slot or two for authentication.
Right.
But it also needs to limit how many it's willing to spend, because it's a denial of service.
That's right.
Right. So I think it would be very interesting. It would be very interesting to write this up as a document. I would be very excited to work on that. So thank you.
Yeah. So thank you for those comments. Yeah, that is, if there is some information.
My name is Michael Richardson.
There is some information available. Yes, that can be made use of here. That's very good. So there are some limitations to this policy, that I've not mentioned in this presentation, but there are limitations to this policy. In certain cases, certain nodes may not be able to join the network ever. So for example, if a new node comes up over here, let's say an N7 node comes up over here and it tries to attach to the border router has only 3 neighbor table entries, then it's going to get rejected always. There is no alternate. So there are a lot of assumptions here. Yeah. So it assumes that the net density is sufficiently okay to work with.
So is it possible to also evict some entries on board router?
Yeah. So the only eviction that can be done is for the parent nodes, but as Michael mentioned, evicting a direct child will have a ripple effect. Eventually it will result in the complete node or the sub DODAG getting rebalanced. So that is something which has to be avoided because it will result in a larger control overhead.
Yes, Zhen Cao again. So I think this case, because board router is supposed to have a larger memory, right? So the problem you just described actually is not.
Well, you know what? Yeah, let's. In this case, maybe in some cases, border router has a larger memory. Not necessarily in all the cases. For example, in my case, the pilot program that I'm working on, the border router, the platform used here is exactly same as any of the other node. It has the same. So it just has a USB connectivity to Linux here, or some other platform here. But this platform remains the same as these platforms. But yeah, this depends upon deployment to deployment.
Mohit, I do think we should have a draft on this, just to get all the details.
Sure. Thank you.
Okay, so any more comments? So
Thank you.
So thank you. Yeah. Oh, we're pretty 5 minutes earlier than scheduled. Any more question, comments, or suggestions? No. Any more? Anybody doesn't sign the blue sheet? I can pass it through. Then the meeting is adjourned. Thank you. Thank you for attending.
So